Again, I'm trying to define what we mean by the composition of two maps. Suppose you are given two maps. So now let's say, I'm going to use the general map notation. Okay. So now let's say F is a map from A to B, and another map. So now let's say G from B to C. The requirement is that the codomain of the map F is the domain of the map G. I want to repeat. The requirement is that the codomain of map F is the domain of map G. In this case, we can talk about the composite of the two maps. The operation is called the composition. And then the composite, we say the composite of F and G. Okay, the composite of F and G. The notation for the composite of the two maps is denoted using very shortly you are going to see why, but the notation is kind of in reverse notation. Okay, the composite of F and G is denoted by the composite. You write G first. Okay, G circle and F. Again, I'm trying to define the composite of two maps in general. Now suppose you have a map F from A to B and a map G from B to C. The requirement is that the codomain of map F is the domain of G. Okay. In this case, we can define the composite of two maps. Okay. The composite is denoted using, I want to repeat the term. This thing is called the composite of F and G. The notation is in reverse order. So do you know what I mean? We call that the composite of map F and map G. Okay. And then the composite is, the domain for the composite is A. Okay. And the codomain of the composite is C. The definition is as follows. Very shortly, everything will make sense. So just copy down the definition first. Okay. The rule to specify a map, you specify the domain and the codomain, right? The domain of the composite is A. The codomain of the composite is C. And I'm going to give you the rule. Okay. The rule is given as follows. Every element in the set A, every element in set A is mapped to a member of set C or an element of set C. So the same thing. Okay. So just copy it down. Everything will make sense soon. Okay. So the output in C is given by you get the output for the input of X under map F first. So do you see if F is in A, F of X is in B, right? For any member in B, you can apply the map G. Okay, and then you get the output for the input of F of X under G. That is the rule. Okay, it's kind of so how about I'm going to show you the meaning using another diagram. Very shortly, I'm going to show you the meaning using a particular question. Okay. Okay. So now let's say if you have a map F from A to B, I told you map F is a map from A to B. A is the domain and B is the codomain. Okay. And you also have a map G. G is from B to C. They're kind of connected. You have a chain. For the people who are in calculus, so that's why we call it chain rule, right? So you have a chain. Okay. I mean, G is a map from B to C. For the people who came in late, I will tell you what I'm doing now. Okay. Now suppose you are given two maps. Now you can just look at here. Map F is from A to B. The domain of F is A. The codomain of F is B. Okay. So basically, F will map every element in A to a member in B. Okay. And likewise, G is a map from B to C. Okay. And then you connect the two things, and then you have the composition. You have the composite. We call the composition. We call the operation the composition. We call the new map the composite. Okay. Okay. I will show you the meaning. Okay. Under map F, every member in A goes to a member in B, and the member in B, if the map is F, the member in B is f of x, right? F of x is the notation for the output for the input of x in A, right? So because f of x is a member in B, for any member in B, you can apply G to get the output of f of x. Under G, the output is going to be in C. It's kind of f of x now is a member in B, okay, and then you get the output. So by that we mean f of x is mapped to a member in C under G. Okay, so the output is G of f of x. So that's how it works. So do you see in the definition, the rule is given by every member of x in A is mapped to a member in C. It's defined as G of f of x. I hope it makes sense now. Okay. Still, I'm going to show you another particular case using a particular question. Now I think you can also see why the notation of the composite is in reverse order. So do you see it's in reverse order? So because the output is G of f of x. So that's why the notation for the composite is G circle f. You write G first. You write f after the circle. So the whole thing is still called the composite of f and G. When you say it, you say f first. Okay. Simple. I still want to leave this here. So how about I will show you a particular question. Okay. Now, for example, if I give you two maps, so how about they both from R to R? Okay. So now let's say I give you a map F from the set of all the real numbers to the set of all the real numbers. The set of all the real numbers. R2 is the set of all the vectors with two components, right? If I give you the rule for F, so now let's say is so how about every real number is mapped to the square of the number. Okay, so that's how I define F. So that's one of them. If I give you a new map G, so which is also from R to R, okay, which is also from R to R, and then the rule is given. So how about the following? So now let's say every member. Why do I keep on writing 2 from R to R? From the set of all the real numbers to the set of all the real numbers. Okay. So how about for every real number R, it's mapped to. So now let's say for every real number. So now let's say X, it's mapped to it's whatever you want. So how about 3 times X, 3X. Okay. Now I will use that to show you the meaning of the composite of F and G. Okay. The composite of F and G. Okay. Actually, this X. Now look at the mouse cursor. It's kind of a dummy notation. It means, so try to understand me. Okay. It means what is the output for every input. This x can be replaced with any other notation. For the people who are in calculus, I think that the notation could be u. Okay, I still want to use x to show you what's going on. Okay, again, this x here is a dummy notation. I said dummy, D-U-M-M-Y, right? Dummy notation. So by that we mean the notation can be replaced to u to whatever other things. Okay. Now let's try to figure out the composite. So first of all, the composite is going to be a map from R to R, from the domain of F to the codomain of G, from R to R, right? The most important thing is to figure out the rule. Okay. So we'll do it as follows to make it simpler to understand. F is from the set of all the real numbers to the set of all the real numbers. Okay. And I don't need this little 2. And then G is a map from R to R, right? As well. That's G, right? Now you connect F and G. You connect F and G, so you have a chain. It's kind of a chain, right? And then the composite is going to be from that R, the domain of F, to the codomain of G, the composite. Okay, so basically the result of the chain. And then we figure out the rule. Okay, we figure out the rule. So for every input in the domain of the composite, which is also the domain of F, X is mapped under the definition of F. You look at the mouse cursor here. Under the under F, every real number is mapped to the square of the number. So you have x squared. Okay. That's not the output for the composite. Okay, you guys are smart. You tell me something. Okay. Under the map G. So do you want to tell me the output for the input of x squared? You look at the definition of G. G maps every number in R, every real number, to 3 times the number. So just tell me the last thing. If I write a question mark here, so anybody want to tell me the question mark? Yeah, it's 3 times x squared. I was looking for 3 times x squared. Okay. So I think you know what's going on. So by that we mean, you see under G, every input, the output for every input is 3 times the input. So do you see that? Okay. In particular, under G, for the input of x squared, you take 3 times x squared. Okay. So that's why in many cases it's kind of useful to interpret the meaning. Now let's say to interpret G as every input is mapped to 3 times the input. That's how you get output. So does that make sense? Okay. That's the composition of maps in general. Okay. I haven't told you the final answer to the question yet. So the final answer, if I'm looking for the composite is something like, remember to use the proper notations. It's the composite of F and G. You write F and G in reverse order. Okay. So this notation is for the composite of F and G. Okay. And in this particular case, the domain is the domain of F, so which is R, and then the codomain is the codomain of G, so which is also R, right? I'm just trying to use a simpler case for numbers to show you what's going on. Finally, the composite maps every real number to, you look at the end of the 2 chains. I mean the 2 ends of the chain. Okay, every number x is mapped to 3 times x squared. So that is a composite. Actually, for the people who are in calculus, it's kind of the composite of two functions. One function is f. F is defined as x squared, right? And the g g of u. I think the notation we use in calculus, we use u to denote the variable. Okay, g of u is kind of, so now let's say 3u, right? The notation we use in calculus is something like for the people who are not in calculus, you don't have to know what I'm talking about. So basically, y as a function of u is g of u, and u as a function of x is f of x. So we can talk about the composite of two functions. To differentiate the function, we have to use the general, right? It's the same composite. I'm trying to say you are not doing anything new. You are not doing anything new. Okay, the things are consistent. So can I say consistent? Okay. For this course, the main thing we're talking about now is the composition of linear maps. So very shortly, you're going to see the composite of two linear maps is also linear. Okay, and in addition to that, we can get the matrices associated with the linear maps. Okay, I will show you what's going on. In this process, I will also tell you why. So do you remember I told you a long time ago, I promised you to tell you why the matrix multiplication is defined that weird way. Okay, so today is the day I'm telling you why. Okay, it's related to the composite of linear maps. To show you what's going on, I will do one of the questions 1 and 2. So which question do we want? How about we do question? So we do question 1. Okay. Probably I'm going to skip question 2, right? As long as you know what's going on with question 1, then the two questions are similar. Now you look at the question. In the question, you are given two linear maps. Okay, so these two maps are linear. T1 is from R3 to R2. So you see every vector in R3 with 3 components is mapped to a vector, I said R2. Now let me try again. Okay, T1 is from R3 to R3. Okay, every vector in R3 is mapped to a vector in R3. So the rule is given by that. It's linear. Okay. So maybe I should have specified it's linear maps, so you do not have to verify. Okay. And T2 is also linear. It's from R3 to R2. Okay. Every vector in R3 with 3 components is mapped to that. So the output is a vector in R2. The first thing we do is to get the matrices associated with T1 and T2. There's a typo in here. It should be the matrices. I'm looking for two matrices. I mean matrices. We'll do the questions one by one. Okay, we'll do question A first. Question A is old thing. Okay. Now let's recall every linear map is associated with a matrix. The way to find the matrix, so do you want to recall what we did last time? Actually, you did that on the quiz too. Okay. To get the matrix, all we need is to get the output for the standard basis vectors. Okay. Now let's do that first. Okay. Now to do question A. So maybe under T1. I will read the full sentence. Under T1, T1 is from R3 to R3. Okay. To get the matrix associated with a linear map, we need to get outputs for the standard basis vectors. Okay. Under T1, we'll get I write in columns. I think I prefer to write in something like this. Standard basis vectors, one vector R3 I mean, okay, one vector is 1 0 0, the second vector is 0 1 0, and then the third one is 0 0 1. I'm trying to write ij and k in R3, okay, but I'm not using ij and k. So because it's easier to figure out the outputs if I use that form. This one is simple. It's just for x value of 1, y value of 0. You look at the mouse cursor, okay? The rule is given, the definition of t1 is here. So the rule is here, okay? X value is 1, y value and z values are zeros. I believe the output is 1 0 1, is that right? You double check. So let me know if you see anything wrong, okay? X value is 1, y value is 0, z value is 0, okay? 1 0 1. And 0 1 0 is mapped to, I'm trying to say the same thing in different ways, or you can say goes to 1 0 1 0 goes to, or it's mapped to, okay? Y value is 1. I think you have 1 1 1 0, is that right? 1 1 0. The last one, I guess I do not have to look. You are going to have 0 1 1. 0 1 1. So why we do that? We want to get the matrix associated with T1. To get the matrix, we need to get the outputs for the input, for the inputs of the standard basis vectors. Okay, now the notation, you look at the last line, you look at question D. I'm going to use A to denote the matrix associated with T1. A is the matrix associated with T1, okay? So maybe, because it's in question D, so I'm going to write the meaning of A, okay? Now let A be the matrix associated with T1, associated with, okay, T1, I mean T1. Then we have T1, okay. Okay, just write, squeeze T1 in here. So T1 is, I still need to figure out T2, of course, okay. T1 is a 3 by 3 matrix formed by the outputs of ij and k. By that I mean the first column consists of 1 0 1, and the second column 1 1 0, the third column 0 1 1. So that's not T1, so sorry, I should have used A. We are going to use A to denote the matrix, right? If you know what's going on here, then I'm going to figure out T2 a little bit quicker, okay? So T2 is actually, so maybe under T2. In order to get the matrix associated with T2, we need to get the outputs for the standard basis vectors in that R2. You look at mouse cursor in the domain of T2, okay? So you have 1 1. So you need to get the output for 1 0 1 0 0. I mean 0 1 0. The third k is actually 0 0 1, right? So basically 1 0 0, x value is 1, y z values are zeros. I think the output for the input of 1 0 0 is 1 0. So let me know if you see anything wrong, okay? So please. And then I think you have output for the input of j is -1, 1. And then the output for the input of k, z value is 1, 0 0 -1. Again, so let me know if you see anything wrong. Okay. Can squeeze the two things in here. I'm going to use AB to denote the matrices associated with T1 and T2. More precisely, you have to include something like respectively. Okay. I think you know the meaning. I'm trying to save space here. So I have B. B is the matrix associated with T2. T2 is a linear map from R3 to R2. So T2 should be a 2 by 3 matrix, right? 2 by 3 matrix formed by the outputs of ij and k. The first column you have 1, 0. The second column you have -1, 1. The third column, of course, you have 0, 0, -1. That's how we get B. That's the old stuff. Now question B is new. Question B is new. Okay. Question B is for two linear maps, we are going to get the composite of T1 and T2. We work on question B now. Okay. I think from past years, I think people like the chain thing better. Okay. I'm going to use the chain stuff. Okay. So now let's say T1 is from R3 to R3. It's more intuitive to use the chain stuff. Okay. And then T1 is from R3 to R3, and then you make a chain. Composition is essentially a chain, right? And then T2 is from R3 to R2. The two chains are connected, of course. Okay. So basically, the two maps are connected. Okay. T2 is from R3 to R2. I mean, and then it's below that, you can figure out the rule. Okay. So this is a new thing. Every vector in the domain of T1 has three components. You have x, y, and z. Okay. The output for the input of x, y, z under T1 is simple. You just copy T1. Okay. X plus y, and then y plus z, and then z plus x. The next thing is new. The next thing is kind of new. Okay. Now concentrate. The next thing is kind of new. I will show you two ways to interpret the answer. Okay. I told you x, y, and z are kind of the dummy notations. One way is as you do the following. Under T2, every vector, so now let's say whatever notation you want to use. So now let's say A, B, and C is mapped to, again, x, y, and z are dummy notations. By that I mean x, y, and z can be replaced with anything. You could use A, B, and C. You could use U, V, W, or whatever thing. Okay. So A, B, and C are mapped to A minus B, right? And then the second component is y minus z, so which means b minus c. Is that right? So correct me if you see anything wrong. Okay. Why do I do that? If you do that, you can treat the first component as A, and then you can treat the second component as B, and then you can treat the third component as C, and then now let's say the first for the output under T2, the first component is going to be A minus B. You just compute A minus B. You replace A and B with x plus y. You replace B with x plus z, and so on. So do you know what I mean? So that's one way to see that. Okay. In any case, the second way to see that the second way to see that, I can leave it here of course. Okay. The second way to see that is how to interpret T2. Okay. In terms of components, so do not use x, y, and z. You listen to me carefully. Now you listen to me. Okay. Under T2, the first component in the output is the difference between the first two components in the input. So does that make sense? And then the second component in the output is the difference between the second component in the input and the third component in the input. So do you know what I mean? Either way, it's okay. Actually, to some of you guys, I know, so this way could be simpler. But now we are going to figure out the output for, you look at the mouse cursor, for that input under T2. Okay. Anybody want to tell me the first component? If you can tell me the first component, then you got it. The first component, please. I'm looking for the first component here. So please, if you can tell me the first component, then you got it. X minus z is right. X minus z is right. Okay. Okay. It's okay. I will tell you the meaning. Okay. I'll tell you how you get it. I know all of you guys knows. You just don't bother. Okay. Just don't bother to tell me. Under T2, the output in the first component is the first component in the input minus the first component. I mean minus the second component in the input. You compute the first component in the input minus. Okay, so basically, you compute that the first component in that vector minus the second input of that vector. So you have x minus z. Okay, I think you know what's going on already. And likewise, the second component, I think the second component should be y minus x. So thank you. The second component is y minus x, right? That's not the answer to question B. That's a simpler way to see what's going on. Okay. But for the final answer, I'm looking for the composite of T1 and T2. Remember the notation is in reverse order. So this is called the composite of T1 and T2. Okay. I will write the final answer in here. Okay. So the composite of T1 and T2 is denoted using T2 circle T1, the little circle. Okay. Specify the domain. Specify the codomain. You see the chain. The chain after connecting T1 and T2, the chain, the beginning of the chain is R3. The end of the chain is R2, right? So the composite is from R3 to R2. And then to specify the composite, you tell me the rule. So the rule is something like x, y, z. For any vector in R3, it's mapped to a vector in R2. Now you look at the two ends of the chain. Okay, x, y, z under the composite is mapped to a vector in R2. The first component is x minus z, and then the second component is y minus x. Okay. Any questions? If you get this, you'll know what we mean by the composite of linear maps. Okay. I think we can include question C on the same slide, so that we can see what's going on. Okay. I told you it's also possible to use the dummy notations, replace x, y, and z with ABC for T2, and then to get this, you compute a minus b. Your a is x plus y. Your b value is y plus z. You compute a minus b. So you have that component. Okay. Either way is okay. Either way is fine. Okay. Now we work on question C. Okay. We work on question C. In question C, we are trying to get the matrix associated with T1, with the composite of T1 and T2. Okay. So this time, I'm going to write under the composite of two maps, under the composite of T1 and T2. T2 circle T1. So be careful how we say it, how we write it, in reverse order. Okay. Under the composite of T1 and T2, we need the output for the standard basis vectors. You look at the mouse cursor. In that R3, we still need ij and k, right? 1, 0, 0, that's I, and then 0, 1, 0, that's j, and 0, 0, 1, that's k. Okay. Okay, under the linear map, so this one is mapped to a vector in R2. A vector in R2 has two components. Okay. Now you look at here. You look at the mouse cursor. Okay. You look at the rule for the composite. X value is 1, Y value is 0, Z value is 0. Okay. I think the output for 1, 0, 0 is 1, negative 1. And likewise, the output for the input 0, 1, 0. 0, 1. Y value is 1. X and Z are zeros. So correct me if you see anything wrong. Okay. And the 0, 0, 1. 0, 0, 1. Z value is 1. I think you have negative 1, negative 1, 0, right? Anybody see anything wrong? So if I use C to denote the matrix associated with the composite of two linear maps, I can figure out C now. Okay. C is the matrix formed by the outputs for ij and k. I mean, okay. Okay. C, the first column of C is 1, negative 1, right? It's coming from, so look at the mouse cursor, from the output of 1, 0, 0. Likewise, the second column is 0, 1. The third column is negative 1, 0. That's C. That's how we get C. Okay. Any questions? Essentially, that is the new thing. Question B and C. Essentially, question B is the new thing, right? After you get the composite, you know how to get the matrix. Okay. Amazingly, there's an important relation, between A, B, and C. Now let's recall the meaning of A, B, and C again. A is the matrix associated with T1. B is the matrix associated with T2. C is the matrix associated with composite of T1 and T2. Okay. And you do not have to guess. The relation is indeed here. You look at question D. The relation is on the screen. Okay. Amazingly, there's a relation. C is actually the product of B and A in that order. B. I want to repeat. This is true in general. This is true in general. That's why we define. So try to understand that. Okay. That's why we define the multiplication of two matrices in that way. So just because we want to make BA the matrix associated with the composite of the two linear maps. Okay. If you can get that, then it's better. If you do not get that, it's okay. But try to remember the conclusion. It's true in general. By that I mean, if in the future, of course, if I want you to verify, you have to compute. So, but in the future, for any other purposes, if you need the matrix associated with composite of the two linear maps, all you need is to multiply the two matrices. Okay. So do you see something amazing in here? T1, T2, the maps are something abstract. You need to specify the rules and so on, from R3 to R2, from R1 to R1. Okay. We can but we can represent the linear maps using matrices, using a bunch of numbers. Okay. So that's something amazing. We can use something concrete to represent something abstract. So that's the idea. Okay. Comparable with calculus. So compared to calculus, so calculus are something useful and ugly. I always say that in calculus. Actually, you see, so they think it's pretty, right? Okay, we're done we're not done question 1 yet. Still in question D, it's easy to verify this. We got C, we got A, we got B. Okay. We got A in here, we got B in here. It's easy to verify that. To do question D, all we need is to multiply A and B. We want to get C. Okay. I'm going to complete the solution to the question. Okay. Now question D. For question D, my intention is not to ask you to use the conclusion. Okay. I want you to actually verify. By that I mean, I want you to actually compute the product of B and A. In this case, BA, you copy B, you copy A. Okay. I think on the last slide, B is 1 negative 1, 0, 0, 1 negative 1. 1 negative 1, 0, 0, 1 negative 1, if I remember correctly. So that's B, right? And A is easy to memorize. The next row has to be 0, 1, 1, I think. No. 1, 0, 1. Again, the matrix on the left is B, the matrix on the right is A. And then I want you to actually multiply the two matrices. I want you to actually multiply the two matrices. If you want to show your work, you could show your work, but the answer has to be C. Okay, the answer has to be C. So can I skip that? Again, the answer has to be C. So by that we mean, I want to repeat, it's true in general. Okay. If A is a matrix associated with T1 for any linear map, if B is a matrix associated with T2 for any linear map. Okay. And then you multiply the two matrices in that order. You multiply B and A, so the matrix you get is the matrix associated with the composite of T1 and T2. Okay. Simple. So questions? From that, you can also see the composite is actually a linear map if T1 and T2 are linear. Okay. So we're done question 1. If you don't have any questions, question 2 should be simple. Okay, and we'll work on question 3. How about we start with the matrices? Okay, you can see it's kind of the same thing. For question 3, I think I can do question 3 a little bit quicker. Okay. We'll concentrate more on the new stuff. I will slow down for question B. Okay. It's kind of the new stuff. In question A, we are trying to get the linear transformation. Asset transformation, you remember the term? It's nothing but a linear map from Rn to Rn. If the domain and the codomain are the same, then we say it's a linear transformation. Okay. A simple term. In question A, we are trying to get T sub A. T sub A is the linear map associated with the linear transformation associated with A. Okay. Now the solution, T sub A. The definition: a 2x2 matrix determines a linear map from R2 to R2. For domain and the codomain, it has to be from R2 to R2. If you want to recall something in general, a M by N matrix determines a linear map from Rn to Rm. Right? That's a particular case from R2 to R2. Okay. And can I write the thing in rows? Every vector, I'm still writing columns. Yeah, that's okay. Every vector in R2, every vector with 2 components is mapped to A times xy, right? You treat this one as the product of 2 matrices, the product of matrix A and the column xy. I'm looking for that, the definition, and then each vector in R2 xy is mapped to the old stuff, right? You look at A, you multiply A and xy. I think the first component you have x plus 2y. Now you look at A. I'm not copying this A, okay? X plus 2y, this row, times that column, okay? X plus 2y. And then the second component is 4x plus y. That is the linear map associated with A, the 2x2 matrix. And T sub B is also from R2 to R2, right? B is also a 2x2 matrix. Okay. And the same thing. Each vector in R2 xy is mapped to a vector in R2, now let's say B times xy, right? For the same reason, you can see each vector xy is mapped to B times xy. B times xy. If you look at B, the first component is 2y. The second component is 4x minus y. Is that right? So please let me know if you see anything wrong. I think I got it right. So we're done question 8. So that's 8. We'll move on to B. Okay. In question B, we are looking for the composite of the 2 linear maps. Okay. Can I squeeze this here so I don't have to remember the composite? I'll do this one like this. I will remove the question. So I can look at the composite. Okay. Again, in question B, we are looking for the composite of the two linear maps t sub a and t sub b. Okay. To do that, the composite of t sub a and now I'm doing question B now. Okay, starting from here, I'm doing question B. The composite. How about we still use the chain notation? Okay. Now for question B, t sub a is from R2 to R2. And t sub b is also from R2 to R2, right? We have a chain again, right? The second one is t sub b. So because we want t sub a first, we want to apply t sub a first, and then we apply t sub b. That's my t sub b. Okay, good enough. And then we figure out the rule. Every vector in the domain of the composite. So can I say that way? The domain of the composite is the same thing as the domain of t sub a. We apply t sub a on to xy. You just copy. You look at the mouse cursor. You just copy from here. Each vector in R2, xy is mapped to that under t sub a. Okay. X plus 2y, and then 4x plus y. To get the output for the composite, we need to apply t sub b. We need to apply t sub b to this vector. You could use ABC stuff, or you could use the interpretation. Anyway, in any case, so anybody want to tell me the first component? The first component should be simple. First component, please. First component. First component, please. You look at the row in here. I'm not giving you any hint. Yeah, 8x plus 2y is right. Okay. You look at the outputs for the input of xy under t sub b. Okay. The first component is double the first component in the input, and likewise the second component is 4 times the first component in the input minus the second component. Okay. I think the first component 8x plus 2y is right. You look at here, you double that number, right? The second component in the input, you have the first component in the output. And likewise, the second component is a little bit weird to compute. 4 times the first component and then minus the second component. I don't know. 4 times the first component. You compute that. And then minus the second component. I did something wrong. Four times the first component in the input, 4x. Minus the second component. Sorry, I did something wrong. I'm sorry, so let me try again, okay? 4 times the first component in the input, I mean 4 times x plus 2y minus the second component, 4x plus y. I don't know. I think x is gone. You have 8y. And then plus y. The minus y probably. Okay, the minus y. I think you have 7y. Is that right? 7y. I think that's right. So correct me if you see it's wrong. Okay. Again, 4 times the first component minus the second component is in here. You get the second component of output of that vector under T sub b. So you have the composite. For question B, you are not answered the questions yet. Okay, that's designed to see what's going on. In question B, I'm actually looking for the composite. You have to give me the domain, the codomain, and the rule. So the composite, the notation is T sub B circle T sub A, right? It's from R2 to R2. And then I'm writing down the answer. Okay, the answer is every vector in R2. Thank you, 7y. Every vector in R2 xy is mapped to a vector in R2, which is given by 8x plus 2y. The second component 7y. So that's good. So that's my 8. Okay. So we got B, right? I guess then the next two questions are very similar. Okay, we'll move on to the next question. No, that's not what I want. I want to copy this. Okay, now you look at C. Now in question C, we are looking for the linear map associated with the composite. Now I need to copy down the composite. To get that, you need to get the outputs for and j standard basis vectors in R2. Okay. So maybe we have plenty of room. So maybe under the composite, we want the outputs for and j for 1 0 0 1, right? So 1 0 and 0 1. Now you look at the definition of so basically the rule. You look at the rule for the composite. X value of 1, y value of 0 will give you 8 as the first component in the output. Okay, and then the second component. Sorry, I think I did something wrong. Yeah, that's right. That's right. And then the second component is given by 7y. 7 times 0 is still 0. And then for the output of 0 1, x value is 0, y value is 1. So do you have 2 7? think you have 2, 7. Now for question C, the matrix associated with the composite of two maps is two linear maps, okay, is the matrix formed by the outputs for 1, 0 and 0, 1. You have 8, 0, the first row, the first column, the second column 2, 2, 7. So that's C. Okay. Finally, so can I omit question D? For question D, you need to verify it's indeed true. Actually, for question D, I want you to state and verify. Okay. I did not write verify, but it's a good idea to verify. Yeah, in any case. Okay. You know the relation between A, B, and C. So the relation I told you earlier is always it's always true that C, the matrix associated with the composite of two linear maps, is equal to B times A